Yes, ma'am. Problems from what?
Like a specific problem. I was confused with numbers.
What number?
70.
I didn't bring my book. I'll try to work all of those out and post them. How about that? Okay, chapter 10 is about gases. Something we have not talked a lot about. So we're about to talk a lot about them. Chapter 10. What I'm going to do is I'm going to kind of give you all the definitions, all of the formulas, then we'll go back and work problems. So, of all of the states of matter, gases kind of march to the beat of their own drum. They do whatever they want. Gases also can travel through very small holes, like fabric mass. So don't get me started on that. But gases are composed of particles that are moving randomly and very fast. They will move in a straight line until they collide with something. So they'll move in a straight line until they collide with either the container that they're in or another gas particle. When they do collide, they simply bounce off. So because they simply bounce off, these collisions are said to be elastic. What does that mean? An elastic collision just means you're not transferring energy between the two colliding pieces. Another way to say that is they have no stickiness, so they don't stick together. They just repel each other. So the opposite of an elastic collision would be an inelastic collision. And an example of that would be billiard balls, or when you're playing pool, you shoot the ball, it hits another ball, causes that ball to move. So they're exchanging energy. That's not what gases do though. So when gases collide, they exert a force either on the container or whatever other particle they're colliding with. So we say that these collisions have pressure, or they are pressure, because pressure is defined as force divided by area. So pressure is something we use to quantify gas behavior. First time we've ever really talked about pressure is in the last chapter when we talked about torque. So let's see if I can fit this right here. So the pressure of a gas depends on several factors. We're going to talk about those factors and how they are related to pressure. And I think this helps you in the long term when you're working problems to think about these factors. It'll tell you if you're doing your math right. All right, the first factor would be the concentration of gas molecules. If I have a high concentration of gas molecules, what do you expect my pressure to be? High or low? High, because the more I have, the more they're hitting each other, therefore the more force they're exerting on each other. So high concentration yields high pressure. Vice versa. Right, the next is the volume of your container. Pressure and volume, we'll learn in an equation later, are inversely related. So if my volume increases, essentially my concentration of my gas decreases, if they have more space to move around. So as volume increases, concentration of gas decreases, which leads to fewer collisions. Therefore, that's what those three little dots mean. You'll have a lower pressure. So pressure and volume are inversely related. One other thing. Pressure decreases with increasing altitude. Which makes it harder to breathe if we're used to a higher pressure. All right, so let's talk about some pressure units then. We already know one pressure unit. We used it in the last chapter. It was ATM. Those are called atmospheres. Another common one is millimeters of mercury. Sometimes you'll see inches of mercury. This comes from using what is called a barometer. It measures pressure. How they do that is they'll have a glass tube that's measuring millimeters. They'll have mercury in this pan. When the gases of like just normal air hit that mercury, it'll push it up that glass tubing, and it tells you the pressure of the air in millimeters of mercury. Another one is torr. Torr is just torr. Another one is the Pascal. It's actually your SI base unit for mercury. Most of the time, we'll be using atmospheres, but you do need to know a few pressure unit conversions. One millimeter of mercury is equivalent to 1 torr, so that's easy. Um, 760 millimeters of mercury equals 1 atmosphere, or 764 equals 1 atmosphere. Then 101, 325 pascals is equivalent to 1 atmosphere. I think that your book likes to use kilopascals more often than pascals. So that conversion has a decimal instead of a comma. So it's 101 decimal 325 kilopascals. So go ahead, start learning these. Some of you need to put that kilojoule to joule or kilogram to gram, liter to milliliter on there too. So it pretty much covers pressure. Gases also depend on a few other properties. All right, so these are the properties we're going to use in the equations that I'm going to give you. First is pressure. We abbreviate that with a capital P. And for most all of these equations, we're going to want pressure in atmospheres. The next property is volume. You're going to want it in liters most of the time. Temperature affects my gases. We want our temperature in Kelvin. Remember, to get my temperature in Kelvin, if I start with my temperature in degrees Celsius, I just add 273 to it. Then we want to talk about the amount. We'll talk about the amount in terms of moles, not grams. It'll be represented with a lowercase n in an equation, and it, of course, its units moles. All of these properties are interrelated. So all four of these properties are interrelated. We're about to look at their relationships. When one changes, it affects the others. The first equations we're going to look at are called the simple gas laws to describe the relationship between pairs of these properties. In other words, we're going to look at two of these properties and keep the other two constant. The first law is Boyle's law. It's named after the person that discovered this relationship. And you already know the relationship. It's between pressure and volume. So it's pressure volume. I told you just a second ago that they're inversely related. So if one increases, the other decreases, and vice versa. So the equation for Boyle's law is P1 times V1 equals P2 times V2. So with these equations, you're always looking for the change. Okay, so if I say, okay, at this pressure, it has this volume. If I change that pressure, what would be my new volume? Okay, so that's how these problems will work. If I wanted to graph this relationship, this is what it would look like. It's a graph. It's a graph of two things being inversely related. Next one is Charles' law. It's between volume and temperature. And volume and temperature have a direct relationship. So if volume increases, temperature also increases. All right, so with most of these equations, you can get by using whatever units you want to use, as long as they cancel out. So like I could use milliliters for volume as long as both of my volumes are in milliliters. But that's not the case for Charles' law. For Charles' law, your temperature must be in Kelvin or you will not get the correct answer. I think you'll have to look at graphs in lab next week. That's why I'm including them here. If something has a direct relationship, the graph would be a linear line. One increases, the other increases. With Charles's law came the absolute zero for temperature. or it verifies the absolute zero for temperature. So the absolute zero for temperature is 0 Kelvin. Put a line through that 0 so that you didn't think it said okay. You can never have a negative Kelvin. If you ever get a negative Kelvin, you have done something wrong. I'm not going to write this, so just listen. Charles Law also explains why the second floor of a house or the fourth floor of this building is usually warmer than the ground floor, because when your air is heated, the volume increases, resulting in a lower density. And so the warm, less dense air tends to rise in a room with your cold, denser air on the bottom. Okay. See, all right, next law is Avogadro's law. I bet you can't guess what it relates, or one of its properties. It would never be mold. So Avogadro's law relates volume and moles. It says that they are directly related. So this equation looks a lot like Charles's law, just with volume and moles. Because they have a direct relationship. It again would be, if I graphed it, it would be a straight line. Or I don't guess that's really a straight line, but you know what I mean. So in all three of these, we are assuming that the other two properties are being held constant. So like here, pressure and temperature is being held constant. Number of moles and pressure constant here. Temperature and moles constant here. Okay, so not sure who it was, but someone came after these three men and combined basically all of them together for the combined gas law. So you'll see all my variables are included except moles. So P1 times V1 over T1 equals da 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 da. It's a mixture of Bowles and Charles law. Let me try to get the ideal gas law in. Not 5 minutes that I have left. All right, so with the 4 laws I've just given you, I could combine all of them collectively for one single set of conditions, okay? So somebody used the relationship and they formulated this equation. It's called the ideal gas law. So for your ideal gas law, these problems differ from simple gas laws in you're never looking at a change, okay? You're given variables and you're asked to find the missing one. So P is pressure. It has to be in ATM. V is volume, and it has to be in liters. N is moles, and it has to be in moles. R is your gas constant. It's a constant, so it is always your R for your ideal gas law is 0.08206 liter time atmosphere over mole time Kelvin. Sometimes you will see this rounded as 0.8206 to 821. So either of those works for me. And then your last one, temperature, and it has to be in Kelvin. All of these units have to be this so that they cancel out in your gas constant. Okay, so I'll have 2 or 3 more formulas to give you on Friday, and then we'll start working the actual problems, okay? See y'all then.